Hello and welcome to this FMCAT 2020 talk about our tool paper SWITSS, Computing Small Witnessing Subsystems. So the context of our work is model checking of probabilistic systems, and a very prominent model for specifying such systems are Markov decision processes. So they look a bit like this. We have states, and each state has possibly a number of actions to choose from, and for each action there is a probabilistic distribution about this over the states, which determines the probability for the successor states. So Markov decision processes combine non-deterministic and probabilistic choice in this way, and they are used widely to model probabilistic, compositional, and reactive systems. And in our case, we assume that there is a state called goal and a state called fail, and we're interested in the probability of reaching goal. Now, before having a probability, we need to fix how the non-determinism is resolved. So mechanisms for resolving this non-determinism are called schedulers. And usually one is interested in somehow best case and worst case scenarios, so the maximal and minimal probability that a scheduler can achieve of reaching goal. We're not so much interested in the precise values, the precise maximum and minimum, but rather in threshold problems. So we ask, for example, is it true that all schedulers have a probability of reaching goal that is greater or greater equal lambda, which corresponds to the statement the minimal probability of reaching goal is greater or greater equal lambda? Or is it true that some scheduler satisfies this? So for some scheduler the probability is greater lambda, and this would be equivalent to the statement the maximal probability of reaching goal is greater or greater equal to lambda. And then we have the same two variants for the upper bounded thresholds. Okay, so in this context, we want to compute witnessing subsystems. This is one of the main things that our tool does. A subsystem of an MDP is another MDP that you get by redirecting a subset of the edges of the original MDP to fail. So here we can see an example. And this also may render or may make some of the original states unreachable. And it's not hard to see that in such a subsystem, the probability of reaching goal will be lower for each scheduler than in the original subsystem. And we say that a subsystem is a witness for a lower bounded threshold property, either minimal or maximal probability of reaching goal, if the subsystem itself has a higher probability than lambda, either minimal or maximal again, to reach goal. So this is a witness because we know that both minimal and maximal probabilities will be higher in the original system. So such a system actually witnesses that the threshold property is already satisfied in the original system. Why is it interesting to compute such subsystems? So first of all, they are a natural notion of witness or counterexample in the probabilistic setting, which leads us to one use case, how you may use them. So an engineer may ask, so why is it true that the minimal probability of reaching some error state, say, is higher than lambda in my system that I'm currently modeling? And to answer this question, you may first want to compute a small witnessing subsystem for this threshold property, which hopefully is much smaller and hence easier to analyze. And SWITSS supports this use case by providing configurable and graphical outputs of witnessing subsystems. Another use case is the automated analysis. So several approaches have been proposed that use similar or notions or exactly this notion of witness in their refinement loop. So for example, there is a counterexample guided extraction refinement framework for probabilistic model checking, and also more recently synthesis algorithms have been proposed that use such witnesses, and they profit from small witnessing subsystems. And we have designed SWITSS in order to be can easily be integrated, we hope, in such frameworks as a Python library or as a command line tool. Take a step back and see how minimal and maximal reachability probabilities can actually be computed in MDPs. So here we have a part of an example MDP where the state S0 has 3 outgoing actions, and we want to compute the minimal reachability probability. So what we do is we construct a linear inequality for each action, which basically says that the value in state S0 should be at most the value that we get by applying the corresponding action. And we extend this to the entire state space to yield an equation system which we call AZ less or equal B. And the minimal reachability probability needs to satisfy this system. Now, to compute this vector per min, we can use the following linear program. So per min is a solution of maximizing Z such that Z satisfies these constraints. On the other hand, per max is the solution of minimizing Z such that AZ greater or equal B holds. Now, we're not so much interested in computing the actual values, we're more interested in threshold properties for these vectors, or for the value in the initial state, say. So in previous work, we have introduced so-called Farkas certificates, and they are based on the following observation. We can write the threshold property, or the threshold property per min eventually goal greater or equal lambda is equivalent to the fact, or to the statement, that there exists a Z such that AZ less or equal B holds, and the entry for the initial state is greater or equal lambda. And we have such formulations as satisfiability of an inequation system for all types of threshold properties. And this is nice because now we have a wide range of vectors that we can use to certify that the threshold property is held. We don't need to compute the actual value of the minimal or the maximal vector. And SWITSS has methods to compute and verify all these types of Farkas certificates. Now, what does this have to do with witnessing subsystems? So let us define these sets fmin and fmax as the Farkas certificates for the threshold property min greater or equal lambda and respectively max greater or equal lambda. Then we have the following statement. So there is a vector p in fmin or max with k non-zero entries if and only if there is a witnessing subsystem for the corresponding threshold property with at most k reachable states. So we can relate the non-zero entries in these Farkas certificates to the states that are reachable in the witnessing subsystem. So this lets us, for example, say that if we want to find small witnessing subsystems with few reachable states, we may as well search for vectors in these polytopes that have many zero entries. And this is the key idea that SWITSS uses to compute witnessing subsystems. Okay, let's have a look at the actual algorithms that we use to compute small and minimal witnessing subsystems. So for minimal witnessing subsystems, we derived mixed integer linear programs from the certificate conditions that you've seen before for Farkas certificates. And yeah, we can't hope to do much better than this because the corresponding decision problem is NP complete. But we have derived a new heuristic approach from our method, which we call the k-step quotient sum heuristic, that computes small witnessing subsystems. So the idea is to solve a sequence of linear programs where in this sequence the only thing that changes is the objective function. And so we would like to find vectors that are Farkas certificates and that have a maximal, or that have as many as possible zero entries. But we can't express this as an LP, but what we can try to do is minimize some weighted sum over the entries of the vector. So we start by setting O0 to be just the all ones vector. So all entries have equal importance in a way. And then we solve the LP, and then from a solution of the previous round, what we do is we set the new value of the ith entry to be 1 divided by the old, so the value of the solution in the previous round. And the idea is that values that have entries that have very low values, they will get very high values in the objective function in the next round, because we hope that while now the entries were very small, the value, in the next round maybe we can push it to become equal to 0. So we increase the weight that this entry gets in the minimization. And in SWITSS, we can update both the initial objective and this update function. And we have actually experimented with the other initial objectives, and we have come up with this. So instead of just taking the equal weights initialization, we do the following. So for minimal reachability probabilities, we take O0 to be the inverse of a solution of this LP. So this LP maximizes the sum over all Farkas certificates where lambda is set to be 0. And for max, we take O0 to be the inverse of, also we maximize the weighted sum over the Farkas certificates for lambda 0. And the idea is that states that have a high value in these Farkas, or that can achieve basically high values in this polytope, they are more important, and hence we want them, so we expect them to be in a witnessing subsystem. And states that have low values here, they are assumed, or they are expected to be less important, and are more likely to be pushed out, basically. So they get higher values in the higher weights in the minimization. And this works quite well. So here we have some benchmarks. We plot the threshold. So for increasing thresholds on the x-axis, on the y-axis you see the size of the resulting subsystem. So the smaller the better. You can see for and here the AO is the all ones initialization, and the inf is the new initialization that we just proposed for max. And we stop plotting, so the subscript tells you after which iteration we measure, so after which LP basically. And we stop plotting as soon as they don't change anymore. So you can see that the new heuristic, it achieves better results, so it has lower smaller subsystems, it returns smaller subsystems, and it also stabilizes already after one iteration, whereas the all once initialization takes 2 iterations to stabilize for this example. And here we have a similar example for the min heuristic. Okay, so a new idea that we have implemented in SWITSS is so-called label-based minimization. The idea is that sometimes you don't want to minimize the actual number of states for some application, but you rather want to minimize the number of participating labels in your witness. So as an example, imagine that the system that you're modeling is a compositional system with 3 participating components. And so in the composite system, you have each state has one of these 3 components active, and you label them with the corresponding color. And now now in the subsystem, you want a component to either be fully out, so no color of that component should be in the subsystem, or you want to include it fully. So basically what you're asking for is a subsystem that minimizes the number of colors that it has. And an instance of this idea was used to minimize the commands in a higher level guarded command language. And they also use such witnessing subsystems. And we have extended our methods to support such label-based minimization. So this is implemented in SWITSS. Now, to wrap up somehow, SWITSS has modules for computing and verifying Farkas certificates, for exact and heuristic methods to compute witnessing subsystems, and graphical output of the subsystems. It's written in Python. This gives us access to many existing libraries and tools, and this should make SWITSS easy to use and easy to integrate in existing systems. We also support a number of LP and MILP solvers as backends, and for this we use the interface provided by the Pulp library. So here are the references that I use in the talk, and now I would like to give you a short demo of SWITSS. Okay, so this is a short demo of SWITSS. This notebook is part of the supplementary material of the paper, so you can download it and try it out yourself. So first we load an MDP from a file and set a custom visualization configuration. And we can open the MDP with this command. So you can see that it has 2 actions in the initial state. The rest is probabilistic. There is a fail state and a goal state, and there are some labels which are indicated by these different colors. Okay, so the first thing we do then is to compute the so-called reachability form, given the MDP, an initial label and a target label, which is a pre-processing step that removes all states that cannot reach target or are not reached from the initial state. So we can compute this. And yeah, you can see that nothing has really changed. For every target state, there will be a unique new target state, and all of the old target states will move to this new state with probability 1. Now, witnessing subsystems, the first thing we do is we want to compute exact minimal witnessing subsystems. For this, we use the MILP exact class. So we instantiate it with a mode, either maximal or minimal, and the solver we want to use. And now we can solve the problem for a given reachability form, the one we defined above, and some threshold. We save the result, and we can visualize the resulting subsystem in this way. And you can see here that the grayed out states, they are not part of the subsystem, so it is enough to include this one state here. For maximum probabilities, the Farkas certificate actually has 1 entry per state action pair, and these entries, they are displayed here on the edges. So basically, the entry init action A has value 0.5 in the corresponding certificate that was computed and that underlies this subsystem. Okay, so we can do the same for minimum reachability probabilities. Again, we solve for the same threshold and have a look at the resulting subsystem. And we can see now that the entries of the vector are now on the states. This is the case for minimal probabilities. And now also we have to include these two states, because for minimum reachability probabilities, we need to guarantee that the threshold is met for all actions. So for A and for B, we need to have 0.1 reachability probability. And this is ensured by this this subsystem. Now, the heuristic approach is implemented in the QS heuristic class. We again initialize with the mode, a solver, and now how many iterations we want to run. And then we can solve iter, which means basically we get an iterator over the results for a reachability form and a threshold. And we have a helper function that prints the results. So here we have three subsystems which have the same states and the same value. So the value and states are the same here, and I will explain in a minute what the value actually does. But first we can do the same for minimum probabilities, and here you can see that the subsystem was improved after the first iteration. So the first iteration had a subsystem with 7 states, and then the second already had a subsystem with 5 states. Okay, so label-based minimization. Here we again make an instance of milp exact as before. And then we solve with the labels parameter, where we specify which labels we want to consider. So here we consider blue, green, and brown states as labels, and we want to minimize the number of labels that appear. So let's do it again. Now the subsystem that we compute has 5 states, but it has only value 1 because only one of these 3 labels participate in the subsystem. And we can have a look at this. So you see now that here this left side was chosen. Although the right side could have been chosen, it has only 2 states, but the 2 states are of 2 different colors, and so the left side was preferred because although there are 3 states, they count as 1 because they are of the same color. So this is what label-based minimization is about. Okay, that's it for the talk. Thank you for listening.